Hello everyone, this is Srinivas, Assistant Professor from the Department of EEE. I will be explaining about the subject Basic Electrical Engineering. So in this, I will be discussing about the Module 1, that is DC circuits. In the previous session, I have discussed regarding the basic definitions of voltage, current, power, energy, and the classification of circuit elements. In this session, I will be discussing about the parameters, resistor, inductor, capacitor, and the ideal and practical sources, independent and dependent sources. Okay, coming to resistor. Resistor is a passive two-terminal electrical component that opposes the flow of current and dissipates energy in the form of heat. The voltage current relation in a resistor is given by R is equal to V by I. The relation between voltage and current in a resistor is linear, and the unit of resistance is volt per ampere, or simply it is represented as ohm. In the below figure, we can see the circuit symbol of a resistor and the practical resistance. So as I explained, the property of a resistor is dissipation of energy in the form of heat. So how the energy is dissipated in a resistor? As the electric charge moves through a resistor, it loses potential energy. This energy is converted into heat through frequent oscillations between electrons and atoms in the resistor material. The conversion of electrical energy is called dissipation. The formula for the total energy dissipated is given by E is equal to power into time. From the definition of power, it is given by the product of voltage and current, which is equal to V into I into time. As there exists a linear relation between voltage and current in a resistor, so voltage is directly proportional to current, or it is given by the product of V equal to R into I. So from this, by substituting in place of V, I into R, we get the relation as I square into R into T. So similarly, the same voltage current relation in a resistor can be expressed as I is equal to V by R. So from this relation, substituting the same in the second equation, we get the relation for the total energy dissipated as V square by R into T. Next, coming to the element inductor. An inductor is a passive two-terminal electrical component that stores energy in the form of magnetic field, and it does not allow the sudden change in current. It is also called as a coil, choke, or reactor. The voltage current relation in an inductor is given by V is equal to L into di by dt. The unit of inductance is given by Henry, and the below figure, here it represents the circuit symbol of an inductor, and these are the practical examples of an inductor. Next, as I said, inductor is an energy storage element which stores energy in the form of electromagnetic field, and the energy stored in an inductor is given by the formula E is equal to half Li square, where L is the inductance in Henry, energy E is nothing but the energy stored in joules, and I is the current through the inductor, and its unit is expressed in terms of amperes. So from the definition of power, we have P is equal to dW by dt, or dE by dt, the rate of change of energy. So from this, dE is equal to power into time, where power is given by the product of voltage and current. Next, as seen before, the voltage across an inductor is given by L into dI by dt into I into dt. So from this, we can write the change in energy as dE is equal to L into I into di. So in order to find the total energy stored in an inductor E, it is given by integral of dE, so which is nothing but integral of L I dI. L being a constant parameter, it is given by integral of I into dA. So integral of I is I square by 2. So from this, the total energy that is stored by an inductor is given by half Li square. Coming to capacitor, capacitor is also a passive element with two terminals, and it is an electrical component that stores energy in the form of static field, and it does not allow the sudden change in voltage. The voltage current relation in a capacitor is given by I is equal to C into dV by dt. The unit of capacitance is farad, and these two represent the circuit symbols of a capacitor. And these are the symbols of the capacitors that are practically used in real-time applications. As I said, a capacitor is a passive element which stores energy in the form of static field. And coming to the energy stored in a capacitor, it is given by the formula E equal to half CV square, where V is the voltage across the capacitor and C is the capacitance value in farad, and E is the energy stored by the capacitor. So once again, from the definition of power, it is defined as the rate of change of energy P equal to dE by dt. So from this, energy is equal to P into T. So from the definition of power, it is given by V into I into dt. The current through the capacitor is given by I equal to C into dV by dt. So therefore, dE is equal to CV dV. So in order to get the total energy that is stored by a capacitor E, it is given by integral of dE, so which is equal to integral of CV dV. So C being a constant parameter, integral of V into dV, so which is equal to C into V square by 2. So therefore, the energy stored in a capacitor is given by half CV square. Next, coming to the sources. So sources are nothing but the active elements which supply energy to the circuit. So these sources are classified as ideal and practical sources, and also the sources are basically voltage source and current source. So coming to the first one, the ideal voltage source. An ideal voltage source is defined as the two-terminal device which is capable of providing a constant voltage across its terminals. The voltage across the terminals of an ideal voltage source remains constant and is independent of the load current. The internal resistance of an ideal voltage source is always 0. So this represents the circuit symbol of an ideal voltage source whose internal resistance is 0. In this case, we can observe the output voltage V0 is always equal to Vs. So with this relation, if I draw a graph between the load current and V0, it can be observed that it is always constant, nothing but V0 is equal to Vs. Next, coming to the practical voltage source. A practical voltage source is that in which the terminal voltage across its terminals are not constant. Rather, it varies with the load current. The internal resistance of the practical voltage source has some finite value and it is represented in series with the source. So this represents the circuit symbol of a practical voltage source. So coming to its characteristics, the dotted line represents the characteristic of an ideal voltage source in which V0 is always equal to Vs. But coming to practical source, because of the series resistance, there is a voltage drop across the resistance. So therefore, there is a small drop in the output voltage, so which is given by V0 less than Vs with respect to the load current. Next, ideal current source. So coming to the current source, an ideal current source is a two-terminal device which supplies constant current irrespective of the load resistance. The value of the current will be constant with respect to time and load resistance. This means that the power delivering capability is infinite for this source. An ideal current source has infinite parallel resistance, which is represented by an open circuit which is connected in parallel with it. So this is the circuit symbol of an ideal current source, in which it has an internal resistance of infinity which is connected in parallel across. So coming to the characteristics, in this case it can be observed that, so with respect to voltage or load resistance, the current remains the constant. So nothing but I naught is equal to Is. So here I naught represents the current through the load or output terminals. So coming to the practical current source, a practical current source is a two-terminal device having some resistance connected across its terminals. Unlike an ideal voltage current source, the output current of practical source depends on the voltage of the source. The more this voltage, the lesser will be the current. So the practical current source is represented by this symbol. In this case, we can observe that there exists an internal resistance across the source represented by Rp. So because of this internal resistance, there is some drop in the load current which is given by I naught is equal to Is minus Ir, where Is is the current which is delivered by the actual source. So coming to the characteristics, so with respect to the parallel resistance, nothing but the internal resistance of the current source, there is a drop in the current. So this represents the ideal characteristics of a current source, and this represents the practical characteristics of a current source. Coming to the sources are also classified as dependent sources and independent sources. So the previous sources that I have discussed, that is regarding the ideal and practical sources, they come under the independent sources because they are independent with respect to load voltage or current. So coming to dependent sources, the dependent sources are classified as dependent voltage source and dependent current source. So coming to dependent voltage source, they are further classified as voltage dependent voltage source and current dependent current source. Similarly, in case of dependent current source, these are classified as voltage dependent or voltage controlled current source and current dependent or current controlled current source. So coming to the very first one, that is dependent voltage source. A dependent voltage source is that where the output voltage is dependent on the voltage across any part of the branch. So that is the reason it is represented by K into V. K here represents the proportionality constant or a gain. So next, coming to the current controlled voltage source, this voltage source is dependent on the current through any branch of the circuit, and the proportionality constant is given by resistance. Being a voltage source, the voltage V0 is dependent on the current I. So therefore, this proportionality constant is represented as resistance R. So in the below figures, we can see the actual or practical representation of voltage controlled voltage source. In this case, it can be seen that the output V0 is dependent on input voltage and the constant is given by some mu which is equal to K as shown in the figure A. Similarly, coming to current controlled voltage source, the output voltage V0 is directly proportional to I and the proportionality constant is represented by rho, which is nothing but equal to R. Next. Coming to dependent current sources. So as I said earlier, Current source, dependent current sources are also of two types. One is voltage controlled current source and the second one is current controlled current source. So here the first one, the voltage controlled current source. This current source is dependent on the voltage across any part of the branch or circuit. And coming to the current controlled current source, this current source is dependent on the current through any part of the circuit. So in the first case, the voltage controlled current source, the current I naught is equal to Gm into Vs. In this, Vs represents the source voltage, Vx. So Vx is nothing but the voltage across any part of the circuit, and Gm is a constant. Usually it is termed as the conductance. And coming to current controlled current source, this current source is dependent on the current Ix through some part of the circuit. And the proportionality constant is represented by again K. And these are the circuit symbols of voltage controlled and current controlled current sources which are used practically. These dependent sources are majorly represented or useful in modification of amplifiers by using the semiconductor devices. So in this case, in the first case, we can see that the output current is directly proportional to the input voltage. That is, the source is dependent on the voltage and the proportionality constant is given by some alpha. So which is equal to Gm as I represented in the above figure. Similarly, coming to the current controlled current source, the output current is dependent on the current through some other part of the circuit I, and the proportionality constant is given by beta. So which is equal to the constant K which is represented above. So for this lecture, I have taken the references from Electrical Circuits by A. Sudhakar and Shyam Mohan and Network Analysis by U.A. Bakshi. Thank you.